So dear student, today we are going to discuss new topic called leaf spring. This is part of chapter number 3 in which we are studying the design of machine elements subjected to bending. Right? So leaf spring, basically where do you see the leaf spring? Alright, let me show you the example. So this is classic picture where you can see the locomotive, or you can see the truck basically is carrying the leaf spring, right? Now what is basically function of spring, that you have to understand. So spring is defined as an elastic machine element which deflects under the action of the load and return its original shape when the load is removed. Now see, this is common behavior. हमें पता है कि स्प्रिंग को हम जब प्रेस करेंगे तो वो दबेगी थोड़ी, और उसको रिमूव करेंगे, लोड रिमूव करेंगे तो अपने आप अपनी जगह वापस आ जाएगी. सो दिस इज simply behavior, elastic behavior of an element. So this is definition of spring. Now this behavior offer two advantages. One is it can take the it can absorb the shock, it can apply the force, right? So there are applications where the spring are used to absorb the shock, that is motorcycle, you can say the car, then locomotives, right? Then in other cases it is used to apply the force. Let's say the safety valve on boilers where the spring is applying the force on a valve, right? Even door closer where the spring is in door closer we are using torsional spring, right, which apply the force. So this elastic element that we know as known as a spring is used to absorb the shock and apply the force. These are the two basic functions that you see in the industries. So basically, if we summarize the application, it is used to cushion, absorb and control energy due to either shock and vibration in car spring, railway buffers or aircraft landing gears. So this first application is to absorb the shock, right? It reduces the vibrations, because vibration in machine tools are going to give you a rough surface finish during machining. So it is very important to absorb the vibration, and it is only possible by this elastic element called spring. Now second application is to apply the forces as in brakes. अगर आपने कार चलाई है या फिर बाइक चलाई है तो आप क्या करते हैं, जब भी ब्रेक दबाते हैं तो देयर इज अ स्प्रिंग ओवर हियर विच रिट्रैक्ट बैक, आपकी ब्रेक को क्या कर रहा है, अपनी पोजीशन पे वापस ला रहा है. सो देयर इट इज यूज्ड टू अप्लाई द फोर्स, राइट? इवन क्लच में क्या होता है, क्लच में भी कंप्रेशन हेलिकल स्प्रिंग होती है. बिकॉज ऑफ दैट इज रिमेन एंगेज इन ऑल द टाइम, राइट? इफ यू वांट टू डिसएंगेज इट यू हैव टू प्रेस द पैडल. इन दैट केस it is going to disengage and you can shift your gears, right? So clutch is a classic example where the force is applied by the compressive helical spring. Now it is also used to apply the forces in brakes, clutches, springs and loaded valves. Third application is to control the motion by maintaining contact between two elements in cam and follower, right? Again, if you look at the IC engine where there is a cam and follower, right? So it rotates, that you have studied in theory of machine, right? But to keep the two surfaces contact, you need to apply force, and that is beautifully possible by using the spring. It is also used to measure the force, as in spring balance and engine indicator. If you have studied the mechanical engineering subject, in some of the subject you have seen that when you are interested to find the forces, the spring is used as a balancing element, right? It is also used to store energy like watches and toys. I hope you have played with the toys. You just simply having a like key like this, okay? You turn it up, you simply store the energy in spiral spring and it releases and your toy simply moves, right? These were the old days, right? Nowadays people are using electronic circuit and motors, but there you can say it's a simple example of storing the energy in watches and the toys. If you look at the simply the figure, this is helical compression spring used in clutch and brakes, right? This is helical extension spring, this is conical spring. These are the types of spring are used based on the applications. Now today's topic is basically a leaf spring. So we have types of leaf spring. One is cantilever leaf spring. Now just look at the actual figure. Now how it is constructed. It is constructed by simply combining the very thin strips one over another, right? one over another. So leaf spring is basically manufactured by simply combining leaf one another over, right? So that is why it is referred as leaf spring. We are combining each strip one over another. So this construction is referred as leaf spring. So there are three types. One is cantilever type of leaf spring. Now what exactly means cantilever? It is not having a complete round. Here it is simply work as a cantilever beam. Okay, so its construction is that it is fixed at one end and it is free to move at another end. So whenever load is applied, it deflects like this. So this load is basically adjustment of shock or application of force, right? So it is work as a cantilever beam. In second classification, we are going to call it the semi-elliptical spring, where simply the mirror image, or you can say the cantilever beam is mirrored about vertical axis, right? So we have this kind of construction, right? So this is widely used in automotive. When you have a two complete full elliptical spring side by side or one over another, we are going to refer this full elliptical leaf spring. Now these all three are offering you advantages and disadvantages, right? If you have a very heavy load, let's say, then the cantilever beam leaf spring is widely preferred, right? But for general applications, these semi-elliptical springs are widely used in automotive, right? Even for smithy work, if you have the press, mechanical press, to absorb the shock, they are also using this semi-elliptical spring in olden machineries. Now, multi-leaf springs are widely used for suspension of cars, trucks, and railway wagons, right? Now, multi-leaf means what? More than one leaf. Let's say this is one leaf, second leaf, third, and fourth. Just look at the actual figure, right? So there are many strips are used. Many leaves are combined together to form the leaf spring. So such construction, semi-elliptical spring are used for in suspension of cars, trucks, and railway wagons. So you have a clear-cut idea that mostly the leaf spring are used to absorb the shocks, right? It is used to absorb the shock. Now, what is the construction? The first part that you see, that is the largest leaf, is referred as master leaves. It is referred as master leaf. It is connected to the hook, or you can say from the eye point, right? So here just look at it. It is connected with the chassis, right? So it is not going to separate it. So these main leaves, master leaves, are basically having eye at the both end. दोनों छोर क्या होगा, आई जैसा राउंड सर्कुलर शेप होता है, वहाँ पे हम क्या करेंगे, उसको कनेक्ट करेंगे, राइट. द रिमेनिंग्स आर रिफर्ड एज अ ग्रेजुएटेड लीव्स, राइट. तो धीरे धीरे क्या होगी, ये उसकी जो विड्थ है, लेंथ है, जो वो कम होती जाएगी, राइट. सो दिस रिफर्ड एज सिंपली अ ग्रेजुएटेड लीव्स. नाउ हाउ इट इज़ कंस्ट्रक्टेड एंड हाउ इट इज़ कंबाइंड टुगेदर. सो यहाँ पे सभी को इकट्ठा रखने के लिए व्हाट वी आर गोइंग टू यूज़ द राउंड रिबाउंड क्लिप. Just look at over here. This is what the rebound clips are there. Okay. So they keep all the leaves together. And the center, you have a U-bolt. Look at over here. This is U-bolt. Okay. This is referred as U-bolt. So what U-bolt does? Simply it connect or simply fixes this whole structure, that is leaf spring, with the axle. Otherwise, you cannot have a assemblies, right? So now how it works basically. How this semi-elliptical leaf spring works. So whenever there is a up and down on surface on the road, so because of that the vertical force is applied, and that pass applied to the center. So this is the main portion where the load is applied. Now because the semi-elliptical spring is made up of two cantilever beam. Let me show you over here. It is made up of two cantilever beam, right side and a left side. So whatever load is you are applying, let's say 1000 Newton. It equally bared by both the ends. So here we have to consider 500 and 500. You cannot consider the 1000 Newton load on each end, right? So because simply it's a mirror image of cantilever beam. So here the center portion is going to be a fixed one. So whenever there is a deflection, let me show you over here. When there is a deflection of cantilever beam, it deflects like this. So this part is remain fixed. So here, whenever you consider the U-bolt, which is used to fix this leaf spring with the chassis, that length of leaf spring is not going to deflect. Remember this. Let me show you in this figure. So this part is basically fixed. So that length is not taking part in deflection, but the remaining length, from this point to onwards, the whole length is going to deflect. So this part is work as a solid part. It is not going to deflect. So here in semi-elliptical, whenever you use the U-bolt, it is going to make this length of all the leaves going to be a solid one, right? It is not going to deflect. So we have to subtract that. We cannot consider that length in deflections. Now, you student, you have to remember the construction of this semi-elliptical spring. Here it is written 2L. It's a span of spring. It is referred as span of spring. So why it is referred 2L? So in calculation, in mathematic designing, we have to consider only the half length. That is L. That is L, right? So in design procedure of leaf spring, we need to understand the mathematics and the theory behind it, right? So leaf spring is considered as a beam of uniform strength. This statement is very important. Now what is uniform strength? Let's try to understand. Let's say we have a beam whose cross section is constant. Try to understand this word uniform strength. Strength means a stress. Whenever you apply the load on this beam, let's say this part is fixed, okay? This part of beam is fixed, okay? And I am applying load at this farmost end, right? That is load P, let's say 1000 Newton, just for understanding. Now because of this, it is going to deflect like this. It is going to deflect like this. Now we know that bending moment is always a force and its perpendicular distance. That is, bending moment is nothing but load its distance. Now in this case, the bending moment is maximum going to be at the fixed end. So I can draw like this. I can draw as per the standard of material knowledge, I can draw like this. So this is the maximum bending moment at the fixed end. But what about the stress? So here strength means a uniform induction, or you can say generation of bending stress. It has to be same across all the sections. That is referred as uniform strength, right? So इसका कहने का मतलब क्या है? इसके कोई भी क्रॉस सेक्शन ले ले, वहाँ पे अगर बेंडिंग स्ट्रेस आप फाइंड करते हैं तो वो एक ही आनी चाहिए सभी सेक्शंस में. अगर ऐसा होता है, सो वी कैन गोइंग टू कॉल इट दिस बीम ऑफ यूनिफॉर्म स्ट्रेंथ. लेकिन दिक्कत ये है कि बेंडिंग इक्वेशन जो है, बेंडिंग स्ट्रेस, बेंडिंग मोमेंट डिवाइड बाय सेक्शनल मॉड्यूलस Z. अब यहाँ पे जो बेंडिंग स्ट्रेस है, इट इज़ कॉन्स्टेंटली वेरिंग फ्रॉम the free and to the fixed. So it is gradually increasing to the max value from right to the left, or simply it is reducing from maximum left to right. So here this value of bending stress is simply varying, and hence the bending stress generated in the beam is also going to vary. So we are not able to keep the bending stress of same value at each section. So what we can do to have this sigma b of constant value, that is uniform strength. Okay, what is meaning of uniform strength? Means to maintain same bending stress value at each section of a beam. So how can be possible? It is possible simply by adjusting this section, that is b into t, or it is a b into h if it is rectangle cross section having height h and the width b, right? So what we have to do, we have to increase the width, right? So let me look at from the top. Instead of making a beam of rectangle cross section constantly, we have to make a beam like this, taper beam like this. Just try to see, right? So at fixed end, it is going to be of a heavy section by width wise, but as you move away, the width is gradually decreases, right? Even you can also vary the thicknesses, or you can say the h, right? So you can also vary the h. So by simply varying the b and h, you are varying the z, that is section modulus z, and hence with respect to the change of bending moment m, you are getting constant value of bending stress. So here we referred the leaf spring simply as a beam of uniform strength. That's why just look at over here what we are doing. Just look at the construction. Over here, just look at the height, that is thickness. It is gradually increasing. It is not remain the same, right? And this is why by definition it is says it is a beam of uniform strength. It is simply come from the bending stress equation. We have to do the change in the thickness, that is height, we can say, right? That's why the construction of leaf spring is like this. From the center it is having higher height, or you can say the thickness or depth, but gradually when you move away from the towards free end, it is having a less less thickness, right? So this is to develop a uniform strength, right? So semi-elliptical leaf spring is assumed as double cantilever beam. As discussed earlier, मैंने अभी बोला कि ये क्या है, सेंटर से अगर डिवाइड करेंगे so it's a simply mirror image of one cantilever beam. So there are two cantilever beams. So it's a double cantilever beam. Okay. So it is assumed to be double cantilever beam which is fixed at the axle housing using the bolt and clip that we saw in the earlier figure. That is, this is the bolt. Okay. So this is the clip and bolt. With that we are going to fix the leaf spring with the chassis or axle. Now the design of leaf spring is based on theory of bending. This is important, right? How we are going to find the B and T, which are the main dimension of the leaf spring, right? We are interested in, right? So that is only possible by considering bending, because earlier what we have said is the semi-elliptical spring is double cantilever beam. So whenever say you beam, they are going to be bending, right? So it is based on the theory of bending. And the considering the maximum bending moment on the spring, as discussed earlier in many lecture, you must consider maximum bending moment, or you can say the bending stress. Based on that, you have to find the cross section. You cannot find at the value of minimum. Okay. So here, the first equation comes is the design of cantilever spring. Which one? This one. If you come across this kind of leaf spring where only half or a single cantilever beam is observable, right? In that case, these are the equations, right? तो हमें क्या करना है? ये equation इस्तेमाल करना है, right? Now let's try to understand this equation. What exactly it says? Okay. So here the first equation is bending stress. We are not going to cover how this equation comes. If you want to learn it, you just recall the bending theories in strength of material, right? So here W is the load acting. This is the L, span. Let me draw over here because it is, we are discussing the cantilever beam type of leaf spring. Okay. So this is the load W we are acting, and this is the length of spring. Okay. Now what is N? The number of graduated leaves. 1, 2, 3, 4, 6. So this is the number of graduated leaves. Okay. And what is B and T? Very simple. B is a width. Let's say this is one leaf. So this width is B and its thickness is T. Right. So there are number of leaves together, right? So this is B and T. So we are interested to find B and T, but here there are two variables. So we have to take a relation. Either we have to consider B is equal to 2 times T, 5 times T, 4 times T. Otherwise we are not able to solve this equation because there are two variables, right? So as a part of design, we will always given the safe stress, load and length and the number of graduation of leaves, right? So we have to find the width and the thickness. Now the second equation is the deflection. Now what is deflections? Whenever you a load is applied, its free end is going to move like this, right? From its neutral position, that is no load position, P is equal to 0. Once you applied P is equal to maximum load, it is going to deflect like this, right? So this deflection is a linear movement, right? So that we are going to call delta. So for that, this is the equations. So whenever you are considering design of cantilever spring, please focus on the word cantilever beam. If it is semi-elliptical spring, we have a different equations, right? We are going to discuss in just a moment, right? But these equations are only for simply for cantilever spring, right? But the concept is remain same: 6WL and BT square, 6WL cube and E BT. What is E? E is a modulus of elasticity. It is related with the material. If material changes, this value is going to change. Now let's talk about the second point. If we are involved in design of semi-elliptical spring, which is our area of interest. I repeat, semi-elliptical spring, which is used in cars and trucks, right? Cars and trucks, which carry the heavy loads. Okay. So this is the figure I'm talking about, right? So here, the first case is when we are discussing the design of semi-elliptical spring with one main graduations. So what is this? Is a one main leaf. अगर एक से ज़्यादा है, then you have to use this equation. If it is only single one main graduated or other remaining are the leaves, in that case we have to use this equation, right? Now here have two possibilities. One either is to neglecting the width of the clip. What is width of the clip? This part, this length. Now what's the logic? Why it's saying like this? If you are fixing the leaf spring on an axle by using U-bolt, what will happen? Because you are applying the clamping force, so this much length, as shown in the figure, is not able to deflect. So it work as a fixed end. It work as a fixed end or solid part. So that much length we have to subtract from the calculations, right? So the first part is, if you do not use such U-bolt in semi-elliptical spring, that means from the center position, this length is going to deflect. But if you use the bolt, then this same length is work as a solid part. It is not going to deflect. So we have to subtract from this effective span, right? So the first part is neglecting the width of clip and the width of U-bolt, right? It's the same equation. If you compare this equation with the previous one, it's the same equation. There is no difference, right? Now what is second part? By considering the width of clip or width of U-bolt. Again, what we have, we are going to so in second case, we are considering the U-bolt. So what happened? Because of clamping force, this much length is going to behave like a solid bar. So we have to subtract this much length from the effective length. So only this much length is going to deflect, right? That's why here the E is given, LE, effective length. If you compare this equation with, the only difference is whenever you are going to consider the center U-bolt, in that case we have to consider effective length. That means we have to subtract this much length, half of this much length from the original span. So we are going to have this LE, effective length, right? So again, for the deflection equation, it's the same thing, 6WL cube NEBT cube, right? Again, with the U-bolt, the only difference is only this LE, nothing else. Only LE. Okay. Now, third point is design of semielliptical spring with more main graduated leaves. What does it mean? You can have one more graduated leaves or 3 graduated leaves. Now, why such construction is exist? Whenever you are required to have a more load, let's say the turbo truck, if you observe very closely, they are having more than one main graduated leaves, right? जो एक मुख्य जो spring है, मुख्य leaves है, और main master leaves बोलेंगे उसको, right? वो एक से ज़्यादा होती है. अगर ऐसा होता है, in that case we have to consider this third position of equations, right? So again, in the third condition, we have same possibility. Either you consider ignore the width of the U-bolt or either consider the U-bolt, right? So again, there is a difference in equations. What is this differentiation is? So bending stress in graduated leaves and bending stress in full leaves. So what exactly means? If you have a more than one leaves, main leaves or master leaves, so we are going to find the stresses separately, right? So this bending stress, F stand for full leaves or master leaves. Because they are more than one, we are going to use this equation for finding the bending stress only in full leaves or master leaves, right? But this equation is used for graduated, which are smaller in section, getting smaller and smaller graduated leaves, okay? So these are two separate equations. Here only difference is this one. Here it is 12, here it is 18. The only difference is 12 and 18. 12 means for smaller graduated leaves and 18 for the full or master leaves. If you consider the deflection, again it is 12 PL cube EBT cube. What is this 3F NF 2G? So this is nothing. Simply NF means number of full leaves, or you can say the master leaves, or you can say the main leaves. How many are there? 2 है, 3 है, 4 है, कितनी? और this NG stand for graduated leaves. उतने उसके कितने numbers है? Graduated means कम. We have to consider the remaining one from the master one. Master को ignore करके बाद जितनी भी बचती है उसको हम बोलेंगे graduated leaves. उनकी कितनी संख्या है उसको बोलेंगे NG. Let's say for example, there are 12 total leaves in a given spring, out of which 2 are main leaves, that is master leaves. तो remaining कितनी होगी? 10. So this 10 is NG. and this 2 is NF. Very simple. So that way we have to replace here the NF and NG value, right? Now second option is if you consider the width of the clip, तो क्या करेंगे? The difference is only we have to consider the effective length. So because of availability of this U bolt, the centered location is not going to deflect. So that much length of the spring we have to subtract, right? It is not going to take part in deflection. It is useless, right? You can say. That's why we are going to reduce the effective length, which is taking part in deflection. Okay. So that's why we are differentiating by simply LE. Otherwise, it's having a same equation. Okay. You just look at it. Same equation, except we are simply writing LE, L cube. Okay. Now let's try to solve a numerical to understand how to design the leaf spring. The first problem is find the width and thickness of locomotive spring. What exactly means? Let me draw here. ये है slip spring, right? So हमको क्या solve करना है? We have to find out the width, that is B, and the thickness T. Okay, so find width and thickness of a locomotive spring, leaf spring from following data, right? Overall length is 1000. So this 2L is 1000 millimeter. Okay. Now maximum load is 40 kilonewton. So this 2P is 40 kilonewton. Okay. Now here 2L, total length of the leaf spring is how much it is? 1000 millimeters. So we have to consider L is equal to 1000. That is L by 2. That going to be 500, right? Why 500? Simply we have to consider only this much length as a cantilever beam. So that going to be half of the total span, right? So I can write simply L going to be a 500 millimeter. Similarly, the load which is applied is of 40 kilonewton exactly at the center, right? So as explained you earlier, it is simply replica of cantilever beam. A semi-elliptical spring is a replica of mirror image of two cantilever beam connected at the fixed position, right? So here we have to divide this load in equal proportion. So this 40 kilonewton will be here, P is equal to 20, right? So here P is equal to 20 kilonewton that we are going to use in equations, right? We cannot use 40. Now the tensile stress, the permissible bending stress, or you can say tensile or bending stress in this case are same, because whenever you bend something, the upper fiber either is subjected to compressive stress or tensile stress based on the in which direction you bend, right? So here the safe limit is given as 410 megapascal. Now width of the middle support, that is L1. I'm talking about this one. This length is given as how much it is? 100. Okay. So it is given 100 millimeter. Now the total number of leaves is 10. Total कितनी है? 10 leaves है. We have 10 leaves. Now E is given. E is 2.1 10⁵ Newton per millimeter square. Now ratio of total thickness of spring to width is 2. Try to understand the word. What it says? Ratio of total thickness of spring. So total thickness is this. Total thickness is this, or depth is this. और divide क्या है? Width. So that is B is equal to 2. So we can write like this. The total depth B divided by B is given 2. Okay. Now let's connect. Let's connect this concept over here, because there are how many leaves are there? 10. 1, 2, 3, 4, 5, 10. So the total depth is equal to number of leaves and the thickness of each leaves. So here we have 10 leaves and the thickness of each leaf is T. So I can write the depth is equal to 10 times of leaves. Now here what I'm trying to do here is I am just trying to connect the width of the leaf spring and the thickness. So here I can replace over here. So replacing this D 10T over in this equation. So it is 10T divided by B is equal to 2. So what is the value? So B is basically 5 times its thickness. So here I can say the rectangle section of leaves is like this. So this is B and this is T. So B is basically 5 times T. So using this relation, we are going to solve the problem, right? Now here, what we have is effective length. We have to consider the effective length. So total span is L minus L1 by 4, right? So this is 500 and this is 100 by 2. So total what we have is 450 millimeter, right? So effective length. So what does it effective length means? Let's say this is the span 500, right? We are going to subtract 50. The total is 100. Total is 100. So we are going to take 50 minus, right? So only this much length is effective. This is going to bend, right? So 500 minus 50, it is going to be 450, right? So this is LE, effective length. Now let's find the bending stress. Now the equation is bending stress in a given leaf spring is 6 WLE divided by NBT square, right? So just let's recall how this equation comes. So this is the equation we are discussing, right? We are considering the central U-bolt, right? And this is semi-elliptical spring having only one main graduation. Whenever there is not clearly mentioned how many main graduations are there, you have to consider only one. So we are going with the one situation, right? So here, now this is safe limit is 410 is given to us 6. Now load is 40, so we are going to take 20 as described earlier, right? So that load P, here we have written P, let me write W, okay? So that is 20 kilonewton. We cannot use 40. We have to divide the load in equal proportion to the 2 cantilever beam of a semi-elliptical spring. Now what is effective length is 450 millimeter, that we find out. Now the total number of leaves are 10. Now here, instead of B, we are going to write 5, as we know, right? And into T square. So this come from here, we simply replace B is equal to 5 times thickness, right? From this equation, okay? Now here it is very simple. Now it is T cube. It becomes the T cube, okay? So you can simply solve this equation. T is going to 13.81 millimeter, okay? So I'm going to take it is 14 millimeter. So here B is going to be 70, 5 times 70 millimeter. So the answer is B is 70 and thickness is 14 millimeter. So this is simply the design of leaf spring. Here the width is 70 and the thickness is going to be 14 millimeter. So all of the leaves having same concept, right? Having same width and thickness, but their length is getting reduced from maximum of master value to the lower value. So to make it a cantilever beam of uniform strength, right? So because of this kind of a graduated or trapezoidal structure, we have a uniform generation of bending stress in each leaves, right? Or each section, okay?